So yeah, thank you everyone for coming. I'm really touched to see so many people. So here I'm talking about my journey towards robust and scalable large language models. This is a really important topic to my heart, and in some sense, it started actually before my PhD, right before when I was at the startup. I read this article, As We May Think, and so this is an article from Vannevar Bush, 1945. It describes this hypothetical device, the MEMX, a device to store and index all of humanity's knowledge, and then query it via an associative index. And I thought this is incredible, and a lot of people have tried to build systems following this, but I thought we weren't quite there yet. And I really wanted to see this kind of device come to realization. At that time, I was most passionate about, how that can index and, categorize my personal life's data, not just the world's data. But, after reading this article in 2017, it led me on this quest to start to build the technology for LLMs. Because fundamentally, I think it's like, this is something I feel is a really important technology for, the future of computing. And so when I started my PhD in 2018, as soon as I got there, this massive trend took off where models started scaling extremely quickly, and we saw a rapid flurry of papers. And this spanned many different domains. It started with masked language modeling and even recurrent neural networks, but now we see the large transformers. And I really remember reading in October 2018, that's like a month into my PhD, the BERT paper. As soon as it came out in arXiv, it was really new, and it really kind of changed everything for me. And it might sound obvious now, but the model it introduced was this model where you pre-train web scale data. And so you scrape tons and tons of books, articles, newspapers, Wikipedia, and it has a relatively random pre-training task here. I mean, this masked language modeling task is, I think, pretty interesting, but it has nothing to do with some of the downstream things we actually ended up using it for. So you would take this model and do useful things with it. So I remember seeing Squad 2.0, the remarkable progress it made in question answering. And so just to kind of underscore how impressed I was with the advance of BERT at the time, I mean, the task it was pre-training with, it was a children's game. It's Mad Libs. It's kind of fill in the blanks. And it's quite remarkable that just by playing this game, remarkable intelligence capability would then emerge downstream. So during my PhD, large language models have grown to 10,000x. This is faster than I think any other trend in recent memory that I've read about. And so we were at 100 million parameters or so when I started my PhD, and now there's recent papers that are in the trillions, 1 trillion parameter range. And so my dad actually was working his PhD in the 80s at Berkeley, and so that trend at that time was Moore's law. And so this is 5 times faster than Moore's law. This is tremendous growth. And so I actually feel quite blessed to have been working on a PhD during a time of such tremendous change, which I think is a really unique experience. But there's a variety of different growing pains that emerge as we scale these models. One of the first problems I started to look at was robustness. And so when we scale up these models, we find that they have a lot of problems when we start to deal with real world inputs. I'll talk about this in a very specific form on one of my favorite papers that I'm quite proud about. But in general, this is a real problem we see as we deploy these systems to real-world people. And secondly, scalability. So how should systems therefore support scaling up these models to increase number of parameters and larger data set sizes? Overall, my goal throughout the PhD has converged to how to make LLMs both robust and scalable. And this spans both machine learning and systems. And so as a foundation, I did a series of works here on robustness for large language models. And I'll talk about the code representation learning paper I'm particularly proud about. And then I worked on a series of papers to improve the scalability of these models, right? And so this touched many different aspects, including inference and the hardware-software interface for these models, as well as new topics in high-speed data transfer enable acquisition of large training data sets for these models. And at the end of the talk, I'll talk briefly about some future directions I'm starting to work on and what I'm excited about for the future of large language models. So to start, I will dig into this first paper, Contrastive Code Representation Learning. And this really deals with a really important problem that I found, which is how do we make LLMs robust to input perturbations? This is a really simple example, and it's a toy example, but it's just to illustrate just how sensitive some of these networks are. Here I have the same prompt. I fed it through ChatGPT twice. And in one case, I added a single character, this exclamation mark. Without it, it fairly consistently, about 60 to 70% of the time, will select option one, autoregressive language modeling. And to be honest, I probably would have chosen that too, given how powerful autoregressive LLMs are. But when I add this exclamation mark, it will very consistently choose recurrent neural networks, right? And so this seems like a simple toy example, but in general, we want our systems, like large language models, to be robust to little perturbations in input. And I think one really practical example where we've seen this now is with systems like ChatGPT that are approaching 1 billion active users. Many users leverage techniques called GPT jailbreaks in order to escape safety controls. So here's an example where a user asks a ChatGPT-based system to describe the steps to produce napalm in the words of their deceased grandmother, and it will willingly comply. And so this is kind of concerning that it will happily generate instructions to create a dangerous weapon, right? So to provide safe and secure and robust systems in practice, we do not want LLMs to be sensitive to small perturbations in their input. So this is a really practical problem, but how I chose to study this was in the context of code large language models. And so when we had worked on this, it was a very early area, but now I believe many of you in the audience here use GitHub Copilot every day when you are writing code. And so this is an example of a code language model. And one of the key challenges when we deal with embedding or representing programs in language models is that there are many ways to express a single program. And so here we can take a particular input JavaScript method, and there are many different variations of that JavaScript method that we can run that produce the same exact behavior at runtime. So it'll do the same thing, but the textual representation is quite different. And so we can rewrite a single program in many different ways and have equivalent semantics when we run it. And a lot of prior work actually discussed the sensitivity of code representations to different transformations. So these are all the equivalent programs, so they should do the same thing. And so the representation should be the same, yet we end up with different results. And so this is undesirable. And so we constructed actually a new dataset benchmark called adversarial code clone detection that really demonstrated this problem very clearly. So here we take Roberta, which at the time was a state-of-the-art model, which was then fine-tuned for code representation tasks. And with just 3 code edits that are semantics preserving, it underperforms a random classifier. So you do better by just guessing, basically, than using this model, which is quite remarkable. And so the question in this work is, how do we learn robust representation of code? But the overall goal, right, is how do we enable large language models to remain robust in light of input perturbations? And so the key result is we introduced a new technique called ContraCode that learns robust representation of source code and substantially overperformed this large language modeling technique, in this case, mass language modeling. And what we found is that when we then take that model and then specialize it for a variety of downstream tasks, accuracy improves. So this isn't really just a toy benchmark, but it actually correlates to better improved accuracy on real-world tasks people do care about. And so the key question is, what makes a good code representation? And I think there are lessons we can draw from this when we look at the natural language domain as well. But in the code domain, the key insight was that programs with the same functionality should have similar representations. And so given a particular program here, we want to make sure that it has similar functional equivalent programs. So in this case, a for loop is substituted with a while loop, but we want to minimize the similarity with functionally different programs. One really interesting result we found is that data augmentations from the NLP domain are actually not effective for programs. So the traditional techniques we leverage to improve robustness of these models really aren't relevant in the context of code. And so you can see here that these are really just not valid programs that we get out traditional data augmentation methods. And so one of the key problems now is, where do we get functionally equivalent programs? So in our work, we leverage a compiler, and so we customize and actually generate these samples. I think today it may be possible to actually apply a similar technique using large language models to synthetically generate these variations. And we actually find we can get a large diversity of programs that matches similar distributions to real-world programs using this method, synthetically generating equivalent program sets. And so then we find that it's actually highly beneficial then to leverage contrastive learning as an alternative loss objective in addition to traditional large language modeling objectives to then encode this extra robustness in this inductive bias model. And so contrastive learning is a very clean loss function, which will enable us to pull similar pairs together and push dissimilar pairs apart. And so we can see here, at the end of this learning procedure, it will learn to tightly cluster items from the same class together while pushing different classes apart.
Can you explain again how so you're generating functionally like similar programs, right? And then you're using contrastive learning. Can you say again how you're doing this generation?
Yeah, so I think it's at the beginning of this.
Okay.
This, yeah.
Okay.
So we take a large bank of unlabeled programs from GitHub in this case. This is the same data set you might train a Copilot or Codex model on, but we leverage something which was the Contra Code compiler, which was a customized JavaScript transpiler specifically to take a single source program and produce many functional equivalent variants for a single program. And so we hand-coded rules and leveraged existing rules for program transformations. Again, I think if I were to work on this project today, I think it would be probably most appropriate to actually use the power of large language models to effectively automate this and better match real-world input distributions. But now that you have this set of functionally equivalent programs, so for each given program, you have a set of, say, 4 or 8 similar programs. I mean, if you ran those programs, you get the same result. That's the key insight. We then leverage the contrastive learning technique. And so I'm not going to go into too many details, but it is this instance discrimination loss function that we can then apply that will effectively apply this constraint that we want to maximize similarity between these vectors while minimizing similarity between dissimilar programs, right? These hard negatives. One of the cool things in this work is we found that it was architecture agnostic and in fact can be highly complementary with existing loss functions. And so this is a technique that can be applied to autoregressive language modeling or mass language modeling, or even just new architectures as we evolve. So we evaluated this, and again, in this case, this is a simple type inference benchmark, but this is actually a task people care about. So given a particular TypeScript program, predict all the types in that program, and that's an assistance that you can provide to a programmer. I think what was remarkable is that, again, we get a substantial lift in accuracy. And so here we can see that in top 1, top 5 accuracy compared to kind of state-of-the-art approaches like deep type, where we get an improvement in accuracy. But I think what's most remarkable is that it actually is complementary with traditional language modeling objectives. So these are, you can combine it with mass language modeling or with autoregressive language modeling at high accuracies as well. And so this kind of shows what the model has done. So on the left, we have the Roberta embedding space, and each color shows similar pairs of programs here. And there's some duplicate colors because there just weren't enough colors to render out all the different program variants. But we can see when we combine Roberta and this Contra Code embedding, that's kind of exactly the embedding space you want, that we're robust to program variations. So as you perturb the program locally, right, you will remain still in the same local embedding space, right? But there's still like global semantic meaning to that space. There's several other papers I've worked on in the area of robustness, again, addressing problems like compositional generalization or graph structured inputs. And these are all collaborations with many students here in the lab. But I believe this is still a really important, fundamentally critical domain to work on in the context of large language models. So beyond robustness, I think one really important thing then that came out from much of the early work in large language models is the scaling laws literature, which actually discussed that capability continues to improve as you scale the number of parameters in a model and also the data set of the model. And one of the most important consequences of this is that we need new systems and tools to enable further progress in training these large models and securing these large data sets for these models. So in 2020, I worked on this paper, Checkmate. And it has a pretty interesting title, but basically the TLDR here is how do we train large models within limited GPU memory capacity? And so this is a real problem that I was encountering as I was doing my research, that memory capacity for state-of-the-art GPUs was not increasing. And so this plot is a little out of date, but if we look at the variety of models that were coming out at the time I worked on this project, they were rapidly encroaching upon the memory limit of the hardware available, right? So GPU memory just has been growing considerably slower than the computational density of GPU hardware. And so at the time, without any mitigation, state-of-the-art models would have hit a memory capacity wall, and we would have been unable to further scale these models easily. And so limited GPU memory was slowing progress at the time for new deep learning models, specifically most permanently for large language models. The problem is, how do we efficiently train these large models beyond the memory limits of today's hardware, right? Because if this were possible, this would remove this memory capacity wall as a constraint for development of these new large-scale models. In this work, we actually examine an algorithmic innovation and how can we change the backpropagation algorithm in order to improve its memory efficiency. So today, backpropagation is optimized for computational efficiency and not memory efficiency. We will present a new algorithm that defines a new endpoint here that substantially improves the memory efficiency of backpropagation. And this is, again, for classic work. We actually find how to tailor this approach for novel neural network architectures that people use, like the transformer, to then find the optimal trade-off between memory and computation. And so this work demonstrated it was possible to train with 5 times larger inputs with a small cost increase. And rematerialization or checkpointing in general has now become a very standard approach leveraged in the community to train these large models. So to illustrate the problem, when we directly train these large language models on GPUs, why are they so memory intensive? So here's a simple model of a 5-layer large language model, maybe not very large, but language model nevertheless. We begin training it. During forward propagation, we actually have to save all of these outputs of all these 4 past layers in memory, because we'll need them later, right, for the pentagons at the bottom. So as we compute the gradient, then we can then again consuming these forward pass activations. And so overall memory usage remains high. Prior work has explored the problem of rematerialization or checkpointing here to save memory. And so this technique here considers a pretty simple optimization that as we begin training, if we're about to exhaust our memory budget, we can just start deleting some tensors or some of these layers from memory, and we no longer need to keep them cached. So our memory consumption drops, but it comes at a cost. When we need those layers later, we have to recompute them later, and that comes with an extra trade-off. And so this technique will substantially reduce the memory consumption, but comes at a trade-off. So how do we actually apply this to modern deep learning architectures and large language models? And the hard problem here is how do we choose which layers to recompute and when do we recompute them? Very specifically, the problem I address in this work is finding a general solution to this rematerialization problem. There's been a lot of prior work dating back 20 years in this area of recomputation, rematerialization from the auto differentiation community. However, they generally make specific assumptions about specific architectures. So it's incredibly difficult to apply it, and usually a lot of these insights are outdated. And the challenge is that neural networks have variable runtime for different layers. There's variable memory usage for different layers. And most real-world large language models are nonlinear. Just look at the transformer block. It has a large nonlinearity in it, and so it's actually really important to consider this when you are considering rematerialization. So again, in this work, we considered, can we optimally trade off memory for computation? And we proposed Checkmate, which was a system for optimal tensor rematerialization. So this set a new baseline for what's kind of the best case opportunity gap available when applying rematerialization of real-world neural networks. And so one of the key insights is having an accurate cost model for hardware and a very flexible search space that allows us to jointly optimize rematerialization and how we also then execute the model. We used integer linear programming to solve this. That may have been a mistake to do because I think a lot of papers after this point kind of started to use IOP as a blunt hammer, but it actually worked quite well. But what we then did is we applied approximation algorithms to then find a computationally tractable algorithm to run this optimization task efficiently. I'm just going to focus on the flexible search space because this is something that has stuck a little bit longer in some of the future work that has followed Checkmate. So here we consider a 3-layer neural network. And so how do we represent this problem of rematerialization, which really depends on how do we represent when to compute a tensor and when to store it. And so here we can unroll the execution across time. And so we begin forward propagating and computing the network. And this represents actually an execution schedule across space and time. And so we actually represent this with what we call the R matrix. But essentially, it was this unrolling that was really critical that enabled a lot of challenging optimizations to just become essentially a linear set of constraints and an objective. And so if you want to rematerialize a single layer, that conventionally would have been challenging to represent, but it actually is trivial in this unrolled representation. So we just set a single bit, and now this represents recomputation of a single layer. And so from that, we can derive we can derive a representation of what tensors are resident in memory at what time step, since we can compute memory utilization. So it's really this insight of this unrolling across space and time that enabled the use of linear programming as a method to optimize execution of these networks. Here's an example of an S matrix for a very outdated model, in this case SegNet, but it's only gotten more complex for modern architectures. But this is something that hand optimization would have been very challenging to accomplish for. And so you can see here in this network, it's rematerializing some layers more than once, 3-4 times. So this is something that was relatively unintuitive for us at first. We evaluated this on a variety of different networks. It substantially improved the batches which we could train these models at. And so we can see for some of these models, it can increase the batch size that you can train at by up to 5x. I think what's most interesting is for transformer style architectures, this resulted in about a 2.3x larger batch size that you could train with, as compared to kind of the default training schedule that people utilized at the time, that is caching everything. And so again, for BERT, which at the time was the large language model we had access to, this was a substantial improvement because it meant you no longer had to use distributed computation to train the model on the hardware at the time. So Checkmate's actually gone on to have a lot of impact, and I'm very proud about it. So a lot of the community has started to reference it as kind of a consistent setup and formalization of this rematerialization or memory optimization problem. And also it's defined many of the key metrics and evaluation with which some of the follow-up work has continued to use. I've been lucky to have industry collaboration with several organizations, including the PyTorch team, the Tesla Dojo team, and NVIDIA about productionizing and utilizing these techniques inspired by Checkmate in practical applications. And there's been several academic follow-ups. So I was particularly happy to see this paper, Dynamic Tensor Rematerialization, which Alton, who's also a PhD student now here at the Sky Computing Lab, worked on. And this took ideas from Checkmate and made them actually practical and realistic for dynamic graphs, which is the way we run most programs today. I worked on several other follow-ups in this direction. Shashir, who I've collaborated with very closely over the years, worked on the POET paper with me. And that one is also something I think is very timely and relevant in today's age when we have large models and we want to find ways to personalize them on private data, right? But it leverages similar techniques to Checkmate, just applied in a very different domain. And so to talk about this third phase of my PhD, this takes a slight departure from hardcore systems that directly improve the deep learning frameworks and algorithms for training these models, and instead looks at kind of solving a real problem that I actually encountered directly from my research in large language models. And that was how to acquire and transfer large-scale pre-training data sets. And so this was a project really just to kind of scratch my own itch. As I was training these big models, I found that data sets were growing bigger and bigger. So in 2021, I remember I was trying to replicate GPT-3 1.3 billion. It's a very small model, nowhere near the full scale model because I didn't have access to massive computational resources, but I still needed the data set. And as I was trying to scrape and acquire and replicate the GPT-3 training data set, this was taking far longer than any of my training runs. This was incredibly painful. And each time I was working with this big data set, it was incredibly slow. And so in some sense, this was a bigger bottleneck for me and my productivity as a researcher than the actual scaling capability of the model itself. And so we all know the attention is all you need paper, and I like to revise it. You should now say attention, and now tons and tons and tons and tons and tons of data is all you need. And last year I talked to a friend who was working with the Lion team to develop this training data set for Stable Diffusion. And so this was a massive, one of the largest scale data sets that was curated in kind of an open source fashion. And he had told me that data was really just this new bottleneck for this new age of generative AI, right? So this is absolutely critical to solve these problems of how do we make it easy and high performance to work with these large data sets in practice. And so just as models have continued to scale, data sets have continued to scale, and this is well motivated. There's work such as revised scaling laws from Chinchilla that say you have to jointly scale both the parameters and the training data set size or tokens to achieve optimal performance. And so I think data has been kind of neglected because it's actually really painful to work with these big data sets. The systems for training distributed models has gotten better, but not necessarily for working with big data sets. So I remember moving a large data set. In this case, I wanted to use TPU, so I was moving some of my data to GCP because we got some credits as a lab, and it was just incredibly slow. The tooling was horrible. I was like, the world cannot be like this. How is it possible that the current state of the art for moving big data sets and using cloud computing is just so bad? And if we want to train big models, we need lots of data. And if it takes me, I have to move that data at 20 megabytes per second everywhere, we're not going to be training anything anytime soon. So these slow transfers are really painful. Another thing that was really important was I was budget constrained as a grad student. It turns out egress fees add up very quickly when working with big data sets. So I think everyone thinks about GPU computing or CPUs and VMs as being a dominant cost in the cloud, but actually if we break it down, the cost of moving data sets in the cloud costs a lot of money because you have to pay for each byte of data you move over these networks. So to just move a 70 gigabyte once would have cost the same amount of money for me to start a 34 node distributed cluster for an hour. So I could have done a lot of research in that, with that much compute, I think, but I had to burn that on just the egress. And so this is a really painful problem I had when I was working with these big pre-training data sets in the cloud. So I built Skyplane, and this was a tool to essentially, scratch this itch and solve the problem of slow and expensive data transfer. I'm not going to spend too much time delving into details again of it, but really my hope is that this can enable further future research as we begin to scale out these data sets and enable open research innovation in an area that was traditionally dominated by big industry who had access to these tools historically. And so Skyplane provides faster networking by leveraging actually pretty classic techniques in networking, such as overlay networking. And it also lowers the total egress cost for data transfer too, leveraging techniques like compression and bandwidth tiering. This is an entirely non-academic benchmark, but this is something that comes from our community benchmark. But it's up to 113 times faster for data transfers within a single cloud, and up to 267 times faster for data transfers between clouds. So this is a 1 to 2 order of magnitude improvement in the speed of data replication, and the hope is that this will then make these data transfer problems easy. So yeah, again, in this work, we considered the Skyplane CP tool, and so this is a data transfer tool. I really wanted to package it up and make sure it's really easy to use because this is really to solve real problems for real researchers, right? So it's an open source package. It'll take a few seconds to get started, but you'll see that the experience is just so much better because once the data transfer starts, it's starting now, the data is transferring at 32 gigabits per second, right? Yeah. This is so much better. If I had this when I was doing large language model research, my life would have been so much better because I could have gone maybe 1 or 2 more years. Yeah. There's still time. I don't want to delve too much into this, but this was a paper at NSTI very recently. Here, when we're looking at these single point-to-point transfers, we leverage a variety of different techniques from the networking community to address this problem. I think one thing I really liked was that I was able to utilize overlay routing as a method to optimize this. That was a paper that, this is a community and area that Jain worked on back in the 2000s. So I think it's really, really nice that these classic ideas can actually come and become really relevant today in the cloud today. Just even though networks have changed so much, these ideas are still deeply relevant. So academically, when we evaluate this, it's up to 5 times faster than the best data transfer tools in the cloud. But we've seen users report substantially faster transfers depending on the source and destination and the practical settings that they run the tool. What I'm most touched by is open source adoption. And so there's a big team of people who've been working on this, and I've been really lucky to work with a lot of people on this project. But we open source this project to actually make an impact on real people. And we're approaching 0.5 petabyte of data transfer to date. And we've had contributors from many organizations who have worked on the project and are using it. And I'm really encouraged that there's a lot of actually other academic institutions that have started to use the technology, such as the Broad Institute, or a collaboration we had earlier last year with NASA for moving large-scale Earth science data sets. So my PhD has touched these topics of how do we fix these growing pains for LLMs, and this covers robustness and the scalability of large language models. I'm now trying to start to look towards future directions, and I'll talk a little bit more about the details, specifically what I'm working on in the Q&A, after Q&A. But, as I look forward to LLMs, I think a lot of researchers, first and second years I talk to, feel a little bit, disheartened to see the rapid progress in proprietary closed source LLMs, like GPT. I think Berkeley has been doing phenomenal innovation in open sourcing that technology and making it broadly applicable to people. But I think there's a lot of really fundamental research directions that I would love to see continue to be researched in this area of LLMs. So just in robustness alone, I think LLMs have a massive issue with hallucinations, and this makes the technology actually really difficult to deploy. And so this is actually a fundamental problem, and this needs, like, I think, some serious academic attention to actually address, right? In addition, I worked on compositional generalization for part of my PhD, and I don't see any early evidence that scaling addresses anything to do with compositional generalization yet. And so this is something that's fundamentally unsolved by scaling laws. And so that means that this is something that I think academia can really actually innovate on and solve fundamentally.
Can you elaborate on compositional generalization?
Yeah, I mean, this is generally the task of, like, if I train on small sequences, can I generalize to more complex or longer problems? One really interesting example is there's a language called Tokifona, which has about 200 words. That's the entire vocabulary. Except it's pretty expressive. You can express fairly complex concepts with it. So humans have this really strong ability to kind of take simple building blocks and compose them to really complex, structures. But LLMs struggle fundamentally with this. So you'll train them on problems of, let's say, complexity up to like 64 length, sequences, and then they will not be able to generalize very well to longer sequences. So that's a big problem today. Moreover, I'd love to see the era of LLMs. It's going to continue scaling, but I think we should maybe think about what comes after that, right? So just in contra code, how I looked at other objectives that you can add to the autoaggressive LLM objective, one really interesting area is how can we better enable LLMs to use tools and operate in the real world? Like, these models, in my opinion, represent castles in the cloud. They're kind of removed from the real world, and I would love to see them interconnected into the way we operate and perform our daily lives. And second, again, getting back to that Vannevar Bush piece, how can we better get at this goal of a large-scale associative memory? And specifically, instead of distilling this associative memory into parameter space, can we actually have external associative memory? I believe this is an area of massive potential in the area of large language models. And these are all topics that large organizations are not seriously working on right now. So I think there's massive opportunities still in this area of large language models if you're starting your PhD. And so that concludes the talk portion of my dissertation, and I'd love to get any questions. Thank you.
First round of applause.